This is Sukriti Joshi. Our today's topic for this video lecture session is Wolff-Kishner reaction and its applications. Now, in particular type of organic chemistry, we have certain name reactions. Name reactions plays a very important role in various unit processes also. They are widely used in pharma industries as well as in dyeing industries, in various chemical industries. They are also very important in certain type of manufacturing units. So why they plays a so important role? Various name reactions can be used. Say for an example, formation of alkyl halide, formation of aryl halide, formation of alcohol, formation of carboxylic acid, formation of particular kind of or conversion of one group to another group. So they are the reactions which gives us tremendous benefit in industry, and even they are tremendously or widely used in various industries also. So we need to make sure here that this kind of reactions are very important. So here what we will have is Wolff-Kishner reaction. Wolff-Kishner reaction plays an important role, but first of all we will see that where it is actually used. So this reaction is also known as reduction reaction. There are certain types of reactions. Say for an example, oxidation reduction reactions, normal kind of or substitution reactions, electrophilic reactions or electrophilic substitution reactions, or nucleophilic substitution reactions. That also involves radical substitution reaction. So there are different types of reactions. Depending upon the product that we will obtain, we will get it. So Wolff-Kishner reaction is also known as Wolff-Kishner reduction. So Wolff-Kishner reduction is the reduction of carbonyl compounds of hydrocarbons by heating them by hydrazine hydrate and a base. So what we will have here is basically we will do the reduction of carbonyl compounds to, or they will be converted to hydrocarbons using the hydrazine hydrate and base. So we will provide it here a higher temperature. In this process, C double bond O group gets converted to CH2 group via C double bond N, NH2 and nitrogen gas. So here nitrogen gas will be evolved, but the reduction of carbonyl group will be done to CH2, right? So what we will do here is we are removing the oxygen and we are adding the hydrogen group into it. So this reaction is basically converting the carbonyl groups to methylene groups. The product will contain methylene group while the substrate will contain carbonyl group. So the carbonyl group will be contained, the oxygen from the carbonyl group will be converted into hydrogen of methylene group. To drive out the nitrogen gas, which is a side product of the reaction, it's necessary to use high boiling point solvent like ethylene glycol. So we have to use here a high boiling solvent which is known as ethylene glycol. This is a reduction for aldehydes and ketones. Other reductible or other reducible groups such as carbon-carbon double bonds and nitro groups usually remain unaffected under the conditions of this particular reaction. So we need to make sure that the temperatures, the reagents which are actually used, the things or the particular substances that we are they plays a very important role in this kind of new reactions, and they will give rise to certain products. So if we want desired products, then we have to add the desired substrates or the necessary substrates. We have to provide the necessary parameters to get a higher amount of product. That plays a very, very important role then, right? So here what will plays an important role is number 1, ethylene glycol, number 2, higher temperatures, number 3, what should be there is carbon-carbon double bonds and nitro groups, right? So we need to make sure that here we have to do the reduction of aldehydes and ketones only, okay? So that contains a double bonded groups, or that contains a double bonded carbon, okay? Now let's see how it goes. So as you can see in the image, we have R1C double bond O and R2. It reacts with NH2 and NH2 in presence of KOH, as we have seen in presence of base. It will get converted into R1 double bonded, or R1 carbon double bonded N contains that, or involves it with NH2, and again one R1 group is there. So 2 R1 groups are there, and it will contain carbon with double bonded nitrogen. Okay, so here at last what we will get is that particular group will be removed and H will be added. So C contains, the central carbon contains 2H and 2 R1 groups there, or 2 R groups there. Now let's see what is the mechanism of Wolff-Kishner reduction. That means let's see how C double bond O groups will be converted into our, or will be reduced, how the reduction of that group will be there. So first of all, the carbon which contains carbonyl group, that is C double bond O, will be react, or it will react with NH2. First of all, what it will form is the carbon attaches with 2R and double bonded with N NH2 group. Right? Now what will happen? It will further react with base. At that time, that particular one hydrogen will be removed, and that double bond will be shifted between 2 nitrogen atoms. So H will be removed, forms H2O. The bond, the particular valency which is free, so that valency goes to the nitrogen part, and it will form carbon which contains negative charge on it, 2 R groups, N double bonded NH. So in this manner we will get here an anion. Okay, so that is basically that forms you a H2O. Now what will happen? That particular group, or H2O further, it was there already, right? So it will add H to the carbon atom to remove that negative charge, because one extra electron, the extra electrons are there and that will be utilized there. Okay, so what we will get here is basically carbon which contains one H, N double bond NH, and 2 R groups are there. Now it will further again react with the base. Okay, so at that time 2 nitrogen atoms will be removed as nitrogen gas, as N2 gas, while here the H will directly gets connected to the carbon. So how it will be done? As you can see, first of all, a negatively charged or an anion will be formed. So R1 carbon R2, that also contains one H but contains a negative charge on itself, right? So it further reacts with H2O. So H2O gets converted into 2 parts, H plus and OH minus. So that H plus will attack on the carbon, attaches with it and forms CH2 R1 R2. So in this manner, the C double bond O will be converted to CH2 group. So carbonyl group will convert itself into methylene group. Clear everyone? In this manner, this will be done. So the Wolff-Kishner reaction or reduction takes place in 2 stages. The first step of the reaction is the conversion of carbonyl compound into hydrazone derivative. This happens in two steps. Number one, A, which is nucleophilic attack of the hydrazine to the carbonyl group, and it is the slowest step in the entire reaction, which is why it is called the rate determining step, which is also abbreviated as RDS, rate determining step. Now, in that only, B, that is the elimination of the water molecule, right? So, in the second one, the elimination of the water molecule will be there. So, first step involves two different sub-steps. After this, we will move ahead to the second step. So, here, the second step of the reaction converts the C double bond N or NH2 into CH2 group, and this occurs in three different steps. So first sub-step A, so in that base catalyzed tautomerization reaction of the hydrazone derivative occurs. Step number 2 or sub-step number B, formation of carbanion with the evolution of nitrogen gas. And step number 3, the protonation of the carbanion by water to form the desired product. Let's see the limitations of Wolff-Kishner reactions. Along with advantages, it also gives us certain disadvantages. So the first limitation is the reduction occurs at a higher temperature. Second one, it cannot be used for sterically hindered ketones. And third limitation is, although the process is specific for carbonyl groups, sometimes migration of the double bond takes place instead of expected mechanism of the reaction when undesired product like alpha, beta saturated carbonyl compounds are formed in the reaction. Let's see the examples. The first reaction involves acetophenone or acetophenone will be converted to acetophenone hydrazone, and it will further converted to ethyl benzene. Right? Now, second one involves cyclopentanone to cyclopentanone hydrazone, and that will further reacted or converted into cyclopentane. Right? And the last one is cyclohexanone. So cyclohexanone will be converted into cyclohexanone hydrazone, which is further converted into cyclohexane. Let's see the applications of Wolff-Kishner reduction. So the first one, it has a broad range of applications. Which of them or some of them includes organic synthesis of multi-walled carbon nanotubes, synthesis of functionalized imidazole substrates, etc. They are actually used for the reduction purpose, that how it will be used and where we can actually convert C double bond O into CH2 group. This is all for this session. Thank you so much everyone.